Hello. I'm Hello everyone. I'm Huijiao. I'm a graduate master student from Denmark Technical University. Today, I will present my work about the role of gender as a confounder in PRS. Let's consider human height trait, which is a representative case in complex trait. Briefly, as we know, the prediction incurrency problem could be current linear model don't consider gene-gene interaction, and maybe it oversimplifies gender representation in sexual dimorphy trait. So the focus of this study is to regard gender as a confounder and consider how to address it in nonlinear PRS. Traditionally, gender represents as their one as a fixed covariant, but the effects of gender could be complex. For example, there are different genetic architecture across different gender cohorts, and also there are effects from sex chromosome. And so the simplified gender representation can include this information. So the next step is to consider some high dimension vector. I call it the gender 2 vector. Introduction. Human height is related to gender since we think male usually is higher. So let's see the PCA analysis. The left figure is cornered by height, and the red data point is higher, and the right is cornered by gender. We can see there are similar patterns in the both two figures, which indicate height indeed related to gender pattern in GWAS summary data. So if we can have some method, some like autoencoder, it is a normal deep learning method that can extract gender and height signal from draw summaries. So we can assume the gender and height representation from encoder should be entangled, as you can see listed in the figure. And then next, we need to consider if we want to control effects in nonlinear PRS model, we can design some method, some like regression in loss function to control mutation information between the two encoder. And this is conceptual figures. To be specific, we can consider two-step modeling. The first step is to get some high dimension representation, and then second step is use this representation to do a normal, Lawson, or linear regression model. So in the first step, we can consider the non-linear PRC model uses some like a three-layer MLP as autoencoder to get some latent representation. And the input, definitely it is the GWAS summaries data. It is noted 010101. And then input to the two autoencoder and use gender and height and level separately to get two kind of encoder and get two different representation from this encoder. So we can call it the gender representation or height implementation. And during the training process, we can add a constraint that can control embedding generation. To some degree, we can align or remove gender signal in height representation to get better representation and to do some prediction. So, in summary, our framework includes two parts. The first one is a nonlinear PRS model that uses GWAS summaries data and gender and height label as input, and the training object is to get accurate prediction and control mutual information, and then we can get gender and height encoder according to different control. And the second part is to get explanation from trained encoder representation, and then we can get which steps are important for the complex trait, like human head. In this study, I just use shape value to explain the neural network. It definitely is not right, but we can. This is the initial step to explore how we can use the nonlinear model to explain the step importance. And this is our initial exploration results. Let's look at the heat map, which is the cosine similarity of Java summary data from one by one data point. And the left one is computed from individual height. And the middle one is computed by original snaps, and the right one is computed by gender. The thin female individual will be noted as 0, you can see here, and the same male individual will be noted as 1. So we can see the three figures have similar pattern, which indicate original snap data have height and gender similar, and height and gender similar information are related. So it is correspond with our introduction that gender and header is highly relevant, and the representation of height and gender embedding is entangled. So after training, we can get encoder representation. The upper one is from gender representation, and the lower is the height representation. And the left is that we control the gender and height encoder show more information, and the middle that we don't do anything. And the right one is that we control the gender and height encoder share less information. We can see the left one, we can get two similar encoder, which indicate we share more information, and the right one that we can get less information between gender and the height encoder. You can see there is a shadow corner and is a deep corner. And then we use that representation we get from the previous three kind of control embedding generation to do prediction using Lawson model. This table shows the predictive results both for training data and test data. And here we can say the gender representation can get similar results between training and test data. So maybe we can congruent the gender embedding generalized well and share more information with height encoder. And the predictive results are better both for train and test data, which means gender embedding is not enough. So maybe we can consider use height encoder that can give some different information. And then we can see the height representation for training data. We can say the better is to share more information with the gender encoder, but for the test data, the better is to share share less information with gender encoder, which means we can disentangle gender information to promote height prediction. And some parts of gender representation is benefit for prediction, and some part is not, which highlights the opinion of us that gender could be a confounder, which means some information in the gender representation is the positive effects for the prediction, and some part is not. So it's correspond our initial hypothesis that just model the gender as 0, 1 is oversimplified. So we need to consider another way to get more information representation as a confounder variable, and then design another method to disentangle it. And then we wonder which snaps are important for the prediction that indicate associated snaps with height. We can see the snaps effect size of Lawson model. The left is the density distribution, and we can see the most is near the cell, and the right is the size distribution. The position of snaps are crossed from the ultrasound to sticks from. You can see this part is ultrasound steps in the ultrasound, and this part is in the 6 chromosome of snaps. But in our model, we can find the snaps in ultrasound. You can say both the three encoder ultrasound still informative in gender embedding, and we can observe the comparable effects between snaps in ultrasound and 6 chromosome. You can see here is comparable effects between ultrasound and 6 chromosome. And get more details, we can observe snaps in the 6 chromosome has negative effects for the height embedding. You can see here, we can't observe it in the simple linear model. And those findings are strange, so we will design more analysis to discuss how the gender to vector will affect the understanding for snap selection. So summary, in this study, we consider gender of a confounder problem in nonlinear PRS, and we also develop the related method to control the confounder in representation. But it is an initial exploration, so in the next step, we will further to explore more. And the limitation is the explanation way. We will explore the better way for future selection, because just to use shape that is the method that can't explain the neural network that is black box fooling. And another limitation is that in this study, just a student project, so I just use toy data. But next I will find collaboration to get UK biobank data to do more verification. And next step, maybe we can consider expand to more confounders, because in this study, we just consider the sex or gender, this single confounder. If we can have more confounder, some age, gender, and BMI, something like that, maybe we need a complex method in the representation learning. Thanks. This is acknowledging. My discussion character is Anders and Xintao. Just briefly introduce myself. My research focuses on confounder problem in representation space, and I interested in the genetics protein and so many AI for biology. So I'm finding PhD exploration. If you have interest for me, welcome to connect with me. Thank you. Do you have some question?
Okay, there you go. You're unmuted now. They shouldn't be able to hear you.
Can you hear
You
me?
can ask questions.
Yes. Were you looking at gender, so self-reported gender, or at sex?
Oh, sorry again.
Were you looking at gender or sex? Gender. Okay. Thank you.
Excuse me. Also, there's a question online. That's what do you mean by toy data? Is it simulated data, or what do you mean?
So I don't have resources to the big data. In just use the computation of the, if you remember in the 2080 year, the human height prediction computation.
Okay. Thank you.
So, because if it is
that's to include several hundred individual, so it's a very less data, very small data.
okay, if it is a real data, I was going to ask how you, handle the ethical issues.
Sorry.
Sorry, if there were real data in 2018, how did you handle the ethical issues that comes with primary data collection and all of that, especially when we talk about sex and gender?
In this study, I discuss the gender, because in the traditional PRS model, the gender model as 0, 1 to do a covariant adjustment to control this confounder problem. But in the representation learning, this is another way to do the disentangle this confounder problem.
Okay, thank you. So thank you, everybody. Let's thank you again.